Guys, welcome back to my lecture 2. So this is lecture 2.2. Now we are going to dive into searching approach, and previously we discussed all the terminologies. Please see the previous video if you haven't, because it's extremely important to understand what is going on in here. Okay, so now let's talk about a very general searching approach, extremely general. So I will take a list that contains the initial state, and I will use this to keep track of my current states as well, and I'll explain what I mean. So let's say I have taken this list. Okay, now I am storing the current initial state, which is A. So I'm saying A is here, right? So now what I'm gonna do is I'm gonna say if there is no if there are nothing or no nodes in the list, then return no solution. But I do have a node in the list, so I will say that I will skip this step. Now I will say, okay, if you have a node in your list, then remove that node from the list. I will say, okay, I'm removing that, right? I removed it. And then I'll say if the node contains goal state, then return solution. Now, is A my goal state? By the way, in this thing, let's take E as a goal state. E is the goal state. Okay, E is the goal state. So is A the goal state here? No, it is not. Okay, then we won't return anything, and we will just move on to the next step, which is expand this node and add resulting nodes to the list. Okay, then so I'll now remove this, and I'll say okay, I'll add this thing, right? This is the only resulting node from A, so I'll add B in my list. Now I'll repeat the same thing. I'll remove this. I'll ask if B is a goal state, but it is not, so I'll expand to the next node. Now I have two resulting nodes. I have C and D, right? I have C and D, but currently we are on B, so I will add C and D here. Now how do I choose which one to explore, C or D? Right now I'll choose randomly. Okay, I'll just choose super randomly. So I'll be like, okay, I'll choose C. It's totally random. There's no strategy I'm applying right now. So sorry. So I'll say okay, I'll choose C. So I'll remove C from here, and I'll say okay, I have moved to C. Is C the goal state? No, it is not. So I'll expand C again, right? And this time I'll be like, okay, I have a D, and then I also have an E. So now let's say I randomly choose E. I randomly choose E. Okay, no strategy here, and I don't know if E is a goal state yet. So I was like, okay, is E a goal state? And the answer is yes, right? The answer is yes. So I'll return E. So that is it. That's my searching strategy, or normal searching approach. I went from A till B till C till E, and this was really simple. But the way I was choosing these things were random, right? Now there is one really major problem in this searching approach, and that is let's say I have this arrow that tells me I can go from A till B, right? Now if I say I have this arrow, backwards arrow as well. Now I can go back. Now I can go from B to A as well. So now let's try this. I'll say okay, I have A initially, right? A is my initial state. I'll say okay, um, I'll remove this thing and I'll say okay, now I'm currently at A. Is this a goal state? Is this node a goal state? No, it is not. Then I'll explore the next option, right? Explore what options I have from here. So I have this option of going here, right? So I'll add this in my list, B. Now here comes the problem. When I remove B, B is not a goal state either, right? Goal state is still E. And when I remove B, now I am here. I have three options now. I have this option of going to A, going to C, going to D. Now do you see this problem that we have now this way for going back as well? So what if I choose A? I was choosing things randomly, right? So my program was choosing the states randomly. What if it got unlucky and it chose A? It can happen. There are 1 upon 3 probability, right? So if I go to A, then I just came back from where I started. So when I'm in A, I just came back. Now this thing will happen again. This I can get stuck in this forever loop, right? I will go from A till B, then I will go back from B to A to B, B to A. It is possible, right? It is possible. It is not 100% like probable, but it is possible. There are around 33.3333% chances of this happening. So this is the problem with this approach. I can get stuck with infinite loops, or even if I don't get stuck in an infinite loop, I can still I had already explored it. I'll still explore it again now. No, and that is a bad thing. I'm repeating myself. This is costly, right? What if there was a path cost to these things? What if there was a path cost? $5. Now if I went to from A to B, I was like, okay, my path cost is $5. And if I went back from B to A, then it is now $10 for no reason. I made zero progress, but still I accumulated $10 of cost. So this is not efficient, and we need a much better approach than this. So this is exactly where we introduce another approach, which is called depth first search. Now the thing that is different in depth first search is it has this normal list as well, but it also has an explored set. Explored set. Now note that I am using the word set because a set cannot store duplicates, which means if the set already has an A, then you cannot put another A in it. Okay, if it was a list and I add an A, I can put an A again and again because it's a list. But in a set, that is not possible. That is a mathematical and that is a very basic property of what a set is. Okay, so this is going to be my approach now. Okay, that I have a explode set as well. And what I will do is, when I will have an element here and I will be like, okay, remove this, which means come to A, right? When I remove something from the list, that means I am currently on this now. When something is in the list, that means these are my possible choices. I haven't took these choices. These are my possible choices. Okay, and when I remove something from here, then I am on this thing. I am on A. So please note that. I know you might have gotten a bit confused about it. So when I will be inside of A now, and I will remove it from the list, now I will put it in the explode set. This is would be my approach. Okay, and there would be another thing, in-depth first search, and that would be, previously when I had these elements, I was choosing randomly, right? I was just choosing randomly. Now that is not a very, good strategy. Even that is like, literally, that's not even a strategy at all. I'm just randomly doing things, right? So that is bad. In depth first search, we will actually have a strategy, which would be to use the last one first. Explore the last one first. And that strategy is called last and first out. Right? So if I said, okay, Usher first option was A, B, and then C. Now which one is the last in this list? C is the last. So I will say I will explore this. Okay? And this would be my strategy. In-depth first search. So two new things. First is the list will be LIFO, which is called last in first out. It is, we can also say now this list would be a stack. If you have studied data structures, then you can call this a stack. My list would be a stack now. That's it, simple. Okay, you can remember it from this way as well. So my strategy would be to explore the deepest node first. Now you would be like, wait, Asher. You said we would just take the last element from the list and explore it. What do you mean by deepest node now? It is totally related. It is totally related. When you will choose the last element from the list, that automatically would be the deepest node. And when I will show you an example now, you will understand it more clearly. Okay, so don't worry about that. So I'll just remove all this thing, and I will give you an example of this as well. Okay, so let's say I have the same thing here. Now that we have a set that is called explode states set, so that means my strategy or my instructions to follow would change a bit as well. Previously we were like, start with a list that contains the initial state, but now we would say start with a list that contains initial state and also an empty explode set. And I explained you this set because no duplicates are allowed in a set. Okay, and the reason behind this, by the way, why is it a set? If you ask me, why is it a set? If you really think about it, if I have this condition, right, A to B, and if I was like, okay, explored state is not a set, it is actually a list, and duplicates are allowed now. Now if I was like, okay, from A I went to B, it will say, okay, you have explored A and you have explored B, right? Let's say we have a C also. Now if I choose to go at A again, it will have no problem. It will be like, yeah, okay, that's fine. It is a list, you can have duplicates. But if you will have a set here, it will say no, what are you even doing? I cannot allow duplicates. So you cannot go back, you have to take the C option no matter what. Okay, so this is why we choose a set instead of a list here. Okay, anyways, now my these instructions are a bit similar, except there would be one more step. So I will see if my list is empty, return no solution. Okay, if yeah, then I will just remove the node from the list. And I have explained you, when I remove the element from the list, that means I am then currently in that node, right? If I remove a node from the list, then I am on that node now. But when it is in the list, that means it is my possible choice, but I haven't actually uh, I haven't visited this, right? I'm not currently on this node. Okay, by the way, these are all nodes. Okay, so, and I have explained what is node in the last lecture. So okay, remove the node from the list, and now I will see if this current node contains goal state, then return solution. I've also explained you what is a solution in the last video, where I said it is the complete path, right? It is the complete path. So do remember that this is what we will return, the complete path, if we have found the goal state. And then we will be like, okay, if it is not a goal state, then add the node to the explored set. Now this is the new step. This is something that we previously did not had. Okay, now we have two things. We have a list and an explored set as well. The name of the set is explored, but the data structure is set. So okay, um also one more thing, you must have noticed that we call this list fringe sometimes or frontier. Okay, so because we use either one of these things, I will use the word fringe as well. Now I won't say list and list and list, I will use the word fringe from now on. Okay, so when I am talking about fringe, just understand that I am talking about this list. Okay, so we have a fringe and we have a explored set. So yeah, add the node to the explored set and then expand the node, and after expanding the node, add the resulting nodes to the fringe to the fringe if they are not already. Now this is the important part, this is where we avoid the problem we were previously facing. If they are not already in the list or the explored set, this part is new as well. Okay, so now let's actually try it. Enough talking and definitions, let's actually try this. So I will just move this a bit here. Okay, and say this is my fringe, and this is my explored set. Okay. Okay, so initially my fringe always has the initial node or state. So this has a. I will remove it. I will come here. I will be like, okay, now I've exploded, so put it in explode. Okay. Is it a goal state? It is not. Goal state is E. So then explore the next nodes. So now I will be like, okay, I have B now. I have a choice to move to B. I will be like, okay, move to B. I will put this in explode set now. Okay, now is B a goal state? It is not. B is not a goal node. Then expand and add the resulting nodes. Now I have the option to move to C and D. Now remember the fact that we will use last and first out. And now there is another question. If I am using last and first out, why I am adding C first and the D last? Now that's a choice. This is where we call there are basically two things. Either you can explore alphabetically or you can explore reverse alphabetically. Okay, currently I'm exploring alphabetically, so I will say C comma D. First I will write C and then D. Okay, now this is a last and first out. That means I will take D. I will explore it. I will remove it from the fringe. I will put it here. And currently I am on D. Now this is important. See, we went from A to B. Now we are on D. Okay. Now we would be like, okay, the resulting nodes are F. Now F will be added in the last because C was already there. So I will add F at the last. Now when F is at the last and D is not a goal state, I will be like, okay, move to the F. Now is F a goal state? It is not. When I have moved to F, by the way, I will remove it from the fringe and put it in the explode. Is F a goal state? It is not. Right. So now what I will do? I will be like, okay, what else do we have in the fringe? We have a C. So now I will move to C. I will go back till B, right? From B, now I will try this option of going to C. Okay, so let's try C now. I am on C, remove it from here. Is C a goal state? It is not. Then we will move to E, right? Is E a goal? By the way, first it will be added in the fringe and then it will be removed. Sorry, it will be just like this. Okay, and now we will say E is a goal state. That's it. Now remember this step. If the node contains the goal state, return solution. So what is my solution here? My solution here is from A I will go to B, then I'll go to C, and then I'll go to E. Right? Let's move on to BFS. Okay, by the way, just one more thing. If I just remove all these things here and make it a bit clean, I want to actually explain why why am I doing this with a fringe. By the way, the Answer is very simple, because I know I can do it in head, right? The what is the strategy? The strategy is to go to the deepest node, right? I can do that in my head also. What's the problem? The problem is you can do it in your head, but the reason is you cannot program it. Like, you cannot program, okay, just take whatever is in my head, right? So you have to program it, this algorithm, and to program it you have to use this thing called a fringe and an explode set, and you have to make this a stack, so it uses last in first out um, a strategy. Now this is a very simple way of making it automatically follow this deepest node. But if you want, I can also do it in my head, right? I will be like, okay, A, then B, then any, let's say, um D, then F. This is obviously deep. I'm doing deeper and deeper. I don't need a fringe then, but when I'm doing it just for the theory part. But here comes the interesting part. Let's say I have a something like this, where this is my starting point, this is my goal point. Now you will get confused, because this was very simple. This was a very simple graph, but this means is a bit weird. Now you will get a bit frustrated and confused. So it's always a good thing to use the fringe technique. Put items in fringe and then take them out using last and first out, and you will automatically, do DFS. Simple as that. If you are getting confused, just use this fringe method. Keep track of your fringe. Okay, so I can do the fringe part here as well, but if it will, it will take a lot of time. So um, just let's so this was DFS. Now let's talk about BFS. BFS and DFS have just one major difference, and that is DFS explores things in this strategy where it will say go to the deepest node. BFS says no, don't go to the deepest, go to the shallowest. Now what do I mean? The way BFS works is it will say go here then here, because it is the only option. But now that you have two options, choose anyone. Okay, let's say I choose this. But in DFS the next step of ours would be to go to E, right? Here we will not do this. Here we will say go D. After choosing C, go D, because it is on the same level, so we want to make same level moves. Then it will say go E. Now we found the goal, right? So if it would have, let's say, chosen to, when it was here, if it had chosen D, then C, and then F, and then E. Okay, so it goes in a shallow manner. Now you do, if it is confusing to you the way it is working, then you don't have to worry. Just remember how its fringe works. Its fringe works in FIFO method. You can also call it Q. What is a FIFO method? Nothing. First in, first out. That's it. First in, first out. Last time it was last in, first out. Okay, so let's take an example here. Let me draw a fringe and explode set. By the way, the instructions would be the same. You remember these instructions? It would be exactly the same. Now the only thing that has changed is this. Okay, so we have fringe, we have explode set. first I will have A here. I will say okay, expand upon it. I will put A here, right? Because A is not my goal state. Then I will have B in the fringe. This is my possible choice. And I would be like, okay, remove B from here and move to B. Then I will be like, okay, what are my resulting nodes? They are C and D. And now remember this, it is FIFO method, right? And I am saying I am doing things alphabetically. I am putting stuff alphabetically. Okay, so I will say C and D. If I was doing reverse alphabetically, then I would write B and C when I'm on the same level. Okay, so let's, for this I'll say I'm going alphabetically. So C and D. Now let's say I'm using FIFO, then I will explore C. I will remove here and put it here and explore C. Now my D comes here, right? And what is my next state? It is E. Now where will I go? Same thing, FIFO. What is my first in? It is D. So I will explore D now. Remove it from the fringe, put it here. Now I have E, and what is the resulting node from D? It is F. So what is my first in? It is E. So now I will explore E. Right? I will remove E. And now I know E is a goal state. So I will just end here. Okay. So what were my states expanded? What were my states expanded? It was from A to B to C to D to E. But what was my goal path? My goal path is from A to B to C to E. So goal path is A to B to C to E. So this is how breadth first search works. Okay, it uses the FIFO method. So that's it for this. Now I'll record another lecture where I will do lots of practice questions on these searching strategies, because I know it is not very clear currently. Okay, so currently I have done depth first search and breadth first search, right? Now there is another which is called uniform cost search. And it has a very simple thing. It is like, I will explore the cheapest node first. That's it. And its fringe is a priority queue where the priority is lowest cost. That just basically means explore the cheapest node first. What do I mean by that? So if I take this and if I put it here, and now I'll give it some values. I will say this is 1, this is 1, this is 2, this is 5, and this is 3. Okay, so the way it will work is, let's say I have this list, I have this fringe, and I have this explored set. I have A in fringe, and I will write it this way: A/1. 1 represents the cost of this. Okay, but is the cost of going to A1? No, it is 0. Why? Because it is the initial state, right? Like moving from nothing to A is 0 cost. Okay, so it is a0. I will remove it from here. I will write it here, and I will be here, right? Then I will say, okay, put b1 in French. b1 means b is my choice, and a is, oh sorry, 1 is the cost. This is the only choice, so I will put it here, b1, and I'll come here. Now I have two choices. I have c1 and I have d2. So which one is cheaper? C is cheaper, right? So I will choose this one. I don't care anything. I will just choose C just because of the cost. That's it. So I will remove this and I'll choose C1. D2 will move here, and then what is the resulting thing? It is E3. Now comes the interesting part. In my French, what is the cheaper option? It is D. Even though E is the goal, it is D is cheaper. So I'll be like, I don't care. I will just move to D. From C, I will move to D now because it is cheaper. So I will write it here. And what is the resulting node? It is F5. Now which one is cheaper? It is E. So now finally I will choose E because it is cheaper. Okay, so the way we are working here is we choose the cheapest thing from the fringe. That's it. Choose the cheapest thing from the fringe. That's all. It is super simple. Okay, and we don't care about depth, breadth, or goal, anything. If for some reason, if it had 6 cost and I was on this position, right? I was on this position, I would have chosen F because it was cheaper. Because I don't care how much my goal state is getting delayed. I just want to go cheap. And then finally, when E was the only option remaining, then I would have chosen E. Okay. So this is how the uniform cost search works. Just explore the cheapest thing. Okay. So these are the main 3 searching algorithms under uninformed search. Uninformed search. Okay, so next lecture hopefully would be doing lots of examples, and activity sheet and stuff like that, so we are more and more clear about what we are doing. So see you next time.